Next speaker, Professor Dr. Andrei Kovalevsky. He is a tenured principal researcher at CICECO, Aveiro Institute of Materials. He has nearly 150 publications and has participated in more than 30 R&D projects supported by European Commission and national funding agencies. His research interest includes oxide thermoelectrics, micro and nanostructural engineering of porous ceramics for catalytic applications, composite oxide materials for electrochemical water splitting and photocatalytic applications. He has done pioneering work towards boosting thermoelectric performance in oxides. He will present a talk on the topic exploring the strategies towards enhancing the thermoelectric performance in oxide materials. So please welcome Dr. Andrei Kovalevsky.
Thank you very much, Indrani, for introducing me. Hello to everybody. Good morning. So in this presentation, I decided to focus more on some specific strategies, approaches towards enhancement of thermal performance in oxide materials. We're working mostly with this materials as thermoelectrics, and I will speak about the work performed in our group during the last 3-4 years on this topic. This work also involved a lot of collaborations, which I would like to acknowledge, especially collaboration with people colleagues from physics department, Dr. Luna Ferreira and sort of Florinda Costa, and also our colleagues from Technical University of Darmstadt, with whom we have quite fruitful collaboration already for more than 10 years. So you probably know something about thermoelectric that can be actually used for various purposes like cooling, so-called Peltier modules, or for sensing. No problem. The simplest example is a thermocouple. In our work, we focus more on thermoelectric effect for energy harvesting, namely aiming at converting waste heat to the useful electrical energy. Before introducing thermoelectrics, I think it makes sense to speak a little bit about waste heat. So what is a waste heat? You can see the diagram showing the estimated world energy use. So the waste, so here you can see on the top different primary energy sources like petroleum, coal, etc. So they can be used then in different sectors like transportation, industrial, residential, commercial, and of course they can also be used for electricity generation. All these sectors, they use this energy, but they also produce a lot of waste heat. And this fraction is very significant. And if you look at the amount of coming from each sector to this reject for waste energy, you can see that from electricity generation, actually a significant fraction comes from electricity generation. So we could really from this picture say that probably there the thermoelectrics would be useful. But in fact, we need to look more carefully about regarding the quality of this waste heat. So here you can see some kind of sectorial shares of the waste heat distribution. So waste heat temperature actually could be different depending on the sector where this waste heat is produced. And in electricity production, for example, you can see that the most fraction is the low temperature waste heat, so-called low-grade waste heat, which is somewhat difficult to convert back to any type of the energy. But if we look at the industrial and transportation sector here, the quite significant fraction of the waste heat produced is high temperature waste heat at temperatures above 300 degrees. We also must remember about thermodynamic constraints. So you know that the Carnot efficiency, basically the heat engine, the engine which allows to convert thermal energy to mechanical energy, and then this mechanical energy could be converted to electrical energy with this, which is the most convenient form of energy for us. So this the efficiency depends very much on the temperature difference. Yeah? And of course, whenever we're speaking about the sectors which produce low temperature waste heat, so there the expected Carnot efficiency is very low. So electricity production produces a lot of waste heat, but we cannot expect that thermoelectrics will or any other thermodynamic engines will be very useful to convert this waste heat. But again, for industrial and transportation sector, it's exactly the places where we can think about using the thermoelectric materials. Oh, how these materials work? Let's assume a semiconductor with some charge carriers which behave themselves. That's a very simplified model as molecules of ideal gas. So when it hits one part, this charge carriers of molecules diffuse to the cold part, and in this way, a potential difference can be created. And whenever we're able to maintain a temperature difference across our material, we can generate this. We can move the electrons or holes, like in this case, and in this way, generate the electrical energy. These P and N type materials can be eventually combined in such kind of couple, like a thermocouple, you know. And so we have heat source from one side, we can generate the electrical power. So there are different thermoelectric modules, different configurations, different approaches, but we mostly work on the materials for this functional part, for the thermoelectric legs, exactly the place where the conversion takes place. Of course, since we are speaking about energy conversion, efficiency is a very important issue. So here you can see a very basic equation for thermoelectric conversion efficiency. And to have high efficiency, so what we need high temperature gradient. This part is very similar to the Carnot efficiency part, yeah. And we also have this parameter, so-called ZT, dimensionless figure of merit, which is related to the basic materials properties. And to have high efficiency, we need to maximize, increase ZT as well. So what is ZT? Is basically this. So we have electrical conductivity, we have squared Seebeck coefficient, and thermal conductivity. Sometimes this part, the product of electrical conductivity and Seebeck coefficient, is called the power factor. So we can compare the electrical performances of thermoelectric materials using this power factor. So looking at this equation, you can easily tell me that how we can get good material with high ZT. So we just need to produce a material with high electrical conductivity, high Seebeck coefficient, and low thermal conductivity. But this is one of the main challenges actually for researchers in thermoelectric fields. The problem is that all these parameters, they are interlinked through the charge carrier concentration. There are also other factors, but this is, I would say, the most important. So whenever we are, for example, doping our semiconductor, introducing the charge carriers, indeed we have an increase in electrical conductivity, everything is fine, but at the same time we have a decrease in Seebeck coefficient, and after certain concentration of the charge carriers, we can have this increase in the thermal conductivity, and this all together doesn't work very well, as you can see. So here we can increase, but we also increase here. And eventually we can tune our material, dop, use different approaches, but end up with the same performance or even performance lower than compared to that one in our initial material. So some kind of optimization of the charge carrier is obviously required, which will result in a peak of ZT in a very narrow range of the charge carrier concentration. So oxides actually emerged as promising thermoelectric materials, although some time ago they were considered mostly useless for this purpose. Let's take a look at this graph. So here I put ZT, temperature, and also years, and put as an example some other thermoelectric materials which are considered for intermediate temperature and high temperature applications like simple phases, half Hustlers, silicon germanium alloys, and some other materials. And you can see whenever we are shifting to the right side, to the side of high temperature, what is left is only oxides, because all other materials, all those alternative materials, they cannot operate at high temperature, or in the best case, they require something like protection cap to avoid any interaction of this material with the atmosphere. And during the last 7 years, actually quite significant progress was achieved for oxide materials, reaching the values of 1.5 even for strontium titanate composite, with graphite. But in most cases, the results of the research work that show that we have gradual improvement due to various concepts, but it is not so dramatic drastic as in this case. So there is still a lot of room to improvement, but the good point is that we really have this progress demonstrated. So let's do a kind of very simple SWOT analysis of the oxide materials in general. So the strengths, they normally have large feedback coefficient, they're pretty stable, they are abundant in most cases, and they don't have high toxicity. And again, as I said, there was a demonstrated significant progress achieved during the last decade for those materials. So those weaknesses related to oxides are low mobility of the charge carriers due to mixed covalent ionic bonding, and also relatively high thermal conductivity, because we're speaking about quite simple structures, at least as compared to those traditional thermoelectrics. And also every oxide has oxygen, contains oxygen, which is a light element, and light elements are not very good for the low thermal conductivity. There are some threats related to the devices. Firstly, the high contact resistance in modules. Oxides not something easy to make contact between oxide and any current collector. And also, since we are speaking about the application high temperature, we must think about, we must take into account the compatibility issue in terms of thermal expansion. And well, oxide sometimes they're not very compatible with metallic parts, with other construction materials, and this might result in cracking and exfoliation during operation cycles. And the opportunities are, so we really can, in the case of oxide, we can think about prospects for high temperature harvesting. This is probably the main advantage. We also can think about all oxide modules where all the components are oxide, and this way we can minimize the compatibility issues. And there are those three last, which I wanted to touch a bit more in my presentation: the redox structural flexibility, and also flexibility for various composite concepts. And also very interesting thing, very important thing, is that oxides really allow different processing approaches to be applied. And I would like to speak one of those approaches we use, the laser process, or laser floating zone processing of thermoelectric oxides. This work was performed again in collaboration with our colleagues from physics department, Professor Florinda Costa and Dr. Nuno Ferreira. So what we do here, basically, we have two rods, feed and seed rods, which are, the material is basically a precursor of our material. So we melt the contact between seed and feed rod, and then we can grow the fiber of our, made of our thermoelectric materials, either up or down. And we also can rotate feed and seed rods to improve the homogeneity of the melt here. So, and we can apply this processing also using different atmospheres, during using different cooling rates, and this creates some kind of additional flexibility in terms of the optimization of the properties of the material. So what are those advantages we have and we expect from laser process? First of all, we can achieve really high density, dense ceramics, and this is important for thermoelectric applications. We don't need any crucibles for this process. We also, since we are speaking about processing which are really far from equilibrium conditions, we can expect the formation some of unique microstructures, some unique redox conditions. We can process refractory materials, and this is especially the case of oxide, of course. Lasers also are not somewhat very expensive right now, and we also can have different options like electrical or even magnetic system, laser growth, and application of some specific gas atmospheres. And one more thing which actually doesn't work very well, but probably we can advance this point as well: the possibility to grow thermoelectric legs in various shapes just in one step. So we know the shape we need for a module, and we can grow it immediately by laser. This shape, this length, this thermoelectric leg. So the challenges and bottlenecks, of course, they also exist. First of all, as in the stance, we are speaking about firstly melting material and then solidification. It's difficult to grow incongruently melting materials. We also can expect the formation of different non-equilibrium phases, different factors related to the heating and uniformity, and also take into account material-specific aspects. So material must absorb in the wavelengths of the laser in order to be heated and melted. Whenever, let's now shift to the materials. Whenever we're speaking about the phase composition, we can get some guidelines even from phase diagrams also. As you know, phase diagrams, they are related to the let's say to the equilibrium conditions, and those are not really equilibrium conditions, but still we can use them. And here is the example of so-called 349 phase calcium cobaltite, which is a well-established thermoelectric oxide with interesting properties, P-type material. So I can expect that by growing this material, we will basically freeze this high temperature condition, which correspond to the mixture of calcium oxide and cobalt oxide. And this is what indeed happens. So if you look at X-ray diffraction pattern, so these are just only oxides. Well, very dense fiber, but oxides, they're useless because the conductivity, the electrical properties are nothing. So, and to turn this material to be thermoelectric, we need to apply really a long time and nearly more than 100 hours to eventually perform this desired 349 phase, which forms in this very narrow range of the concentrations and also the temperature. So you can see the microstructural evolution of such fibers, for example, grown fiber, S-grown fibers. They have this very, very nice microstructure, yeah? See, basically the composite of calcium and cobalt oxides. Very nice microstructure, but they are absolutely useless in terms of thermoelectric properties. And only after applying the post-treatment, thermal post-treatment cycle, we can obtain the eventually 349 phase with this grain structure, which performs well. So what kind of electrical performance we can achieve using this method? So the red curve here is a curve corresponding to laser grown materials, and here I put some literature data. Basically, in terms of electrical conductivity, we're somewhere in the borderline between conventional processing and application of some specific method like spark plasma, sintering, hot pressing. So the results are quite good, but still not something really outstanding. The same for Seebeck coefficient. And so when we can eventually compare the power factor of this material grown by laser with the literature data. And again, you can see we're somewhere in the borderline between the conventional processing and application of those specific methods. So actually, we can say that in this case, in the case of 349 phase, laser processing can be used, can lead to the materials with a quite good performance, but still it is not something, the performance is not something outstanding. What about other materials families like calcium manganite based materials? Again, these oxides are very interesting as thermoelectric. And here, good news is that the desired perovskite-based phase, which has this interesting thermoelectric properties, forms immediately after growth. Still, it contains a lot of impurities, but bad news is that even after post-thermal annealing, these impurities, they don't disappear completely, and of course they can affect the performance. Here you can see that even for annealed fibers, we have quite significant chemical inhomogeneities, which, as I will show you later on, they affect the thermoelectric performance. We also found out that using this laser process in the case of calcium manganite-based materials, we can form some very interesting microstructures like dendrites. Dendrites actually are very, very common for laser-grown ceramics, and such kind of core shell structures with the core and shell having essentially the same chemical composition, but different electrical properties. So in this case, the shell is more resistive, significantly more resistive than the core. And we're trying to use this this phenomenon, this effect, to try to find applications for sensor. So you can see that sometimes we are targeting high thermal performance, but eventually we are getting some features which can be really interesting for other applications. We also observed quite significant effects of the pooling rates, the rate at which the material is solidified and is grown. A high pooling rate, so when we grow the material very fast, normally result in the formation of a significant amount of impurities. And speaking about some optimal pooling rate, we should think about something between 10 and 50 millimeters per hour. And this rule mostly works for all oxide materials, at least for a significant part. So what about the electrical performance? Again, the red curve corresponds to our material grown by laser, and some literature data, and then you can see that the results are not so interesting as in the case of 349 phase. So here we are somewhere in between conventional, let's say, processing method. And this actually happens because we cannot avoid, we cannot dissolve those inhomogeneities which exist in our material during processing. Here we need some kind of additional optimization of this process. In fact, we are thinking about using the laser itself for post-thermal treatment without melting of our material. Nevertheless, the advantages of the laser processing, like crucible-less fast processing, although in many cases we still need post-thermal annealing, we consider these advantages quite important to try to build a module based on this laser processed material. So this work was performed with our colleagues from the Institute of Solid State Chemistry from Russian Federation. So here, the construction of this module itself is very unique. It is for radial waste heat harvesting. So the heat source is the tube, and then the thermoelectric legs are oriented in parallel to the tube. You can expect that probably the better higher temperature difference could be achieved if we make them like perpendicular. But this construction actually allows to have quite significant thermal gradients even in this parallel arrangement. So obviously it could result then in a better specific power because we are saving volume of the module. Here, how it looks. The module contains 12 oxide-based couples based on laser processed material. Here, how it looks like in reality. So we need these tubes to deliver water to cool down the cold part. And using infrared imaging, we show that we can have quite significant thermal gradients in this configuration. Here I put some results on our current voltage characteristics and also power of this module. We compare this performance with the materials, let's say the oxide-based modules from the literature. And we didn't achieve something outstanding here, but mostly it was not because of the module design. It was because the output power was basically limited by those calcium manganite-based legs, which had the performance less than expected. And we are now we are trying to integrate other materials, and we still think that this approach can result in very interesting results. So, just let's say summarizing this part of the talk, how we see the future prospects for our work in this direction. So, of course, we can grow materials in different atmospheres, and there we can expect really formation of different microstructure, and also freezing some specific redox states of the cations, module-related issues. And we also bet a lot on composite approach. Actually, what is happening right now, we intend to grow single-phase material, but we always get composite, almost always. But we can also think about growing deliberately the specific composites and the steep temperature gradients and some atmospheric conditions which we can apply during laser processing actually can give a lot of advantages exactly for composite approach. In fact, the redox flexibility of oxides allows to play with composites and their microstructures, even in the case of materials which are processed by more conventional methods. I want to talk briefly also about this. And as you certainly know, such important applications of redox-sensitive oxides like solid oxide fuel cells and many catalytic processes where this redox flexibility, ability to change the oxidation state, works well for a variety of different purposes. And certainly this type of intrinsic reduction oxidation can also have an impact on thermoelectric properties, as we recently demonstrated in one of our earlier work focused on redox promoted strontium titanate based materials. The idea behind was to use redox-sensitive cations to integrate them first to the structure under oxidizing conditions, and then to exclude them using reducing conditions. So we applied this approach for such kind of composition. So the matrix strontium titanate-based material substituted with lanthanum itself is good thermoelectric. Addition of molybdenum as a redox-sensitive additive So first process under oxidizing condition forming this mixture where molybdenum cations are basically already distributed between scheelite and perovskite phase, and then eventually applying the reducing conditions which result in the formation of such composite containing itself matrix, of course, based on strontium titanate, then some part of strontium molybdate perovskite, and eventually molybdenum submicra and nanoparticles. So here you can see microstructural evolution, which happens in this case. So whenever we first here, we have the molybdenum dissoluted in the lattice in different forms. And then after application of reducing conditions, the formation of this nice composite structure, great particles are particles of molybdenum that they can have quite small size, which is very promising for suppressing thermal conductivity due to phonon scattering effects. And we also observe the formation of such islands of strontium molybdate perovskite inside the strontium titanate matrix. These islands are very tiny, they're very small. We're speaking about probably 5–10 nanometers. And again, this could produce very interesting effect on the thermoelectric performance. By XPS, we confirmed that indeed we have a mixture of different molybdenum oxidation states. So we have part reduced to metallic nanoparticles, and we also have part which still retains in the flexible perovskite lattice. So if you would put just molybdenum oxide under the same condition, reducing conditions, it would reduce it completely to metallic molybdenum. And this is not happening in this case because the perovskite lattice allows to retain the part of this molybdenum cations in the still in the oxidation states higher than 0. And so this has an interesting effect in the thermoelectric performance. Of course, I cannot speak a lot in details here because I don't have a lot of time. But so basically, if you compare the matrix itself with pristine material and matrix with molybdenum addition, so we have simultaneous improvement in the power factor and significant decrease in the thermal conductivity. And this happens due to enhancement of Seebeck coefficient due to carrier filtering effects, we think so. And also in the case of the decrease of the thermal conductivity, it happens due to phonon scattering on redox promoted interface. Now we're working on some kind of new design principle of such composites, and we already have very good results. We have our master student, Tiago Paulino, who will present his work on this during poster session today. So if anybody interested, well, you're welcome. So just the last part I wanted to show, so I still have some time. So what about if we look at this approach a bit other way around? Asking if there is any situation where we can add the metallic precursor instead of using, for example, oxides in processing of complex oxide materials. Normally we use for this purpose, we use oxides, carbonates, other salts, whatever, something like this. Is there any case where the adding metallic precursor itself or certain cation has some additional effect? So we know that then it will heat up, it will oxidize, etc. Probably there will be no benefits, but there are some specific scenarios, and one of those is in the case of zinc oxide doped with aluminum. This, if you probably don't know, this state-of-the-art thermoelectric materials and a platform for designing more complex, more sophisticated thermoelectric composites based on zinc oxide. So we can notice that actually the reaction between metallic aluminum and zinc oxide, so alumothermy reaction, is highly exothermic and can proceed even at room temperature. Also, of course, it doesn't proceed due to thermodynamics. If you look at the DTA curve, you can see that the reaction starts at temperatures around 660, the melting point of aluminum, and is associated with evolution of significant amount of heat. So what will happen? It means that in some places for our sample, we will have some local overheating. And this local overheating could be very interesting for different purposes. It could be easier doping of the material, creation some specific grain boundaries, etc. Many effects we can expect in this. And actually, we are now studying this. I'll just show you some first results on that. So we prepared the reference material, zinc oxide doped with aluminum, but prepared from, let's say, conventional precursors like zinc oxide and aluminum oxide. And then there are two cases where we use metallic aluminum powder as nanopowder or micrometric powder. And the results were actually amazing. We applied the same processing conditions for all samples, obviously, to have good reference point, and found out that in the case of electrical conductivity, there was significant increase. So this blue line is a line corresponding to conventional sample, okay? And we had a significant enhancement, also some enhancement in density, because we have this local evolution of heat, somehow they densified our material better. And also some changes in Seebeck coefficients, which evidence that we have quite significant variation of the charge carrier concentration, which means that indeed we have some changes in the doping mechanism. We can introduce more doping at time, which actually in many cases it is advantageous. In terms of the thermal conductivity, we didn't found any significant difference, although we didn't expect. And finally, if we speak about ZT values for these materials, you can see that. So the materials prepared using metallic precursors have much better performance compared to the base materials. And of course, there is a number of ways how we can play with the precursor, the microstructure of oxides, and this way advance their thermoelectric performance. So just briefly, the conclusions. Indeed, the oxide materials are flexible for laser processing. You can produce highly dense materials with interesting performance, but there are some bottlenecks related to the phase purity of these materials. So there are many challenges still there behind. Also, redox properties of oxides can be involved for tailoring thermoelectric performance and designing new composite with high thermoelectric performance. And in some cases, we really can use, consider using metallic precursors instead of oxidized form. This might offer some additional possibilities for structural and microstructural tuning in oxide thermoelectrics. Some acknowledgement to the projects, all of them they're ongoing, focused exactly on thermoelectric topic. And thank to my colleagues, which helped a lot, as this work was performed by a large amount of people. And thank you very much for your attention.
Thank you very much, Professor Dr. Andrei Kovalevsky, for that very interesting presentation on thermoelectric performance in oxide materials. So the question, this session is now open to the audience for questions. Please, do we have any questions? Okay, so just I want to ask, just out of curiosity, like when you showed these slides regarding the calcium manganese oxide and calcium cobalt oxides, right? So can we also have something like calcium iron oxide, like because manganese and cobalt both are like magnetic?
Yeah.
So okay,
yeah, calcium ferrite, you mean, yeah.
Okay, calcium fluoride, okay.
Yeah, calcium ferrite, there are, so itself, it is not very good materials in terms of thermoelectric properties. Of course, we consider this, we also work with these materials for oxygen membranes. There is one problem, this material has a tendency to ordering of oxygen vacancies and transition to brown minerite phase. And this brown minerite phase could have interesting properties in terms of the low thermal conductivity, because this ordered structure, they can really scatter phonons. It's interesting. But in terms of electrical properties, it won't be very, very good. But indeed, we laser processing itself, the way we use it is not limited only to thermoelectric oxides, of course. So whenever it is, it could be considered possible, interesting for any other applications, it could be done. And exactly in terms of this material, calcium ferrite, I don't see any principal limitations which don't allow to grow it. For example, in the case of 349 phase, it is difficult to prepare material because it has a very narrow range of conditions where the phase is stable. Okay, in the case of calcium ferrite, I assume that the range of the conditions is much wider, and of course it is possible to grow.
Okay. Thank you very much. So do we have any more questions, please? So okay, so thank you.
Thank you very much. Thank you very much. It was a pleasure for me.
For these. Thank you very much.